Welcome back, everyone. In this lesson, we discuss message authentication code, in short, MAC. MAC is a tag that can be used to authenticate the message and verify its integrity. Let me give you the concept behind MAC. MAC is also often referred to as a key hash function, simply because it is just like a hash function. The only difference is it is using the key to hash the message. In MAC, sender and the receiver must share a secret key K to compute MAC. So MAC is computed in this way. Take a suitable hash function, and the hash function, you pass in the key K and of course the message M, and the resulting value is called MAC. In short, let us denote it as MAC, MAC. So in use, MAC is computed from message M and a secret key using a suitable hash function H. To authenticate this message, what the receiver needs to do is to use the same key that was used by the sender for computing the MAC, and then compute the MAC of the message that he has received, and then compare against the MAC that he has received. If they both match, it is said to be the verification successful, otherwise fail. So since this secret key is only shared between the sender and the receiver, if the third party who does not know this key cannot manipulate the MAC, because MAC can only be computed by using the key K, and that is how message integrity is achieved. To give you a better intuition about how MAC works, why MAC is called a keyed hash function, let me use this slide, but take note that you don't really need to understand the steps involved given in this slide. This slide is just to show you some of the steps that is involved in a standard MD5 hash function. And this is the figure. This is a figure that shows some set of steps that are involved. The only thing that you need to take note here is the key here, which denotes a 32-bit constant value. And this key value is used as part of the MD5 operations. And there are many various such operations in MD5 algorithm. So if you are not using a MAC, MD5 function will always use the same constant value, so that it always produces the same hash value for a given message. But instead, if you are using a MAC, which is built based on the MD5 function, instead of using this constant value, it will be using the shared secret key that is shared between the sender and the receiver, and that is how MAC works. And that's why you can think of MAC is just like a hash function. It's just that it is computed with a key, and that's why it is called keyed hash function. So let me illustrate the message integrity proof verification process right here. So MAC is computed using a hash function. It can be any standard hash function. It doesn't have to be MD5, the one that I showed earlier. It can also be like MD4 or SHA-1, SHA-2, SHA-3, and so on. And the key K has to be used. Sometimes it is also referred to it as MAC key. And M is a message to be hashed. So assuming that Alice wants to send a message to Bob, so that Bob can verify the integrity of the message, firstly, they have to have a shared secret key, and the key has to be shared through a secure channel. And when we discuss about hybrid encryption, if you recall, we have discussed about a way to establish such a secure channel, and they can use that hybrid encryption technique to exchange this shared secret key. And we won't be touching this in this slide. So just assume that Alice and Bob has already a shared secret key. And now, Alice wants to send this message M, What she will do is she will compute MAC by applying a suitable hash function. It can be, again, it can be MP5, SHA-1, SHA-2, or SHA-3, whatsoever. He will compute, Alice will compute MAC by using a suitable hash function and taking as input the M message M, and the key K. And the resulting value is called MAC. Next, Alice will send both M and the MAC to Bob, so that when Bob receives M and the MAC, he will compute MAC of the message that he received. So this MAC is the MAC of the message that he received, and he has to compute that using the same hash function that was used by Alice and the same key that was used by Alice. And then he will compare against the MAC that he received, and if they match, the integrity verification is successful. Of course, somehow, if along the way this message M has been modified by some attacker, or maybe due to the loss of some kind of data along the way, this MAC will not match to the MAC that he received, and then in that case, the integrity check will fail. Let me explain about why a standard hash function cannot be used to provide the message integrity proof. Why do we need to use MAC on top of the hash function? So imagine that you are using a normal hash function. What will happen is this Mallory guy, instead, he can modify the message first, which will result in an M prime. And then he can also derive the corresponding hash value of that M prime by using the same hash function that was used by Alice. After all, the hash function is the public knowledge. It is not hidden. So he can use the same hash function and compute the corresponding hash value. And then he would discard both M and H, the original message M and H, and then instead he will only replay M prime and H prime to the Bob. So when Bob receives M prime, he will use the same hash function to compute the hash value, and then he will compare against the hash value that he also received. Will this checkout, will this verification be successful? Of course, it will be successful because after all, this H prime is the hash value of the message M prime itself. So when Bob does the same thing, then of course it will result in the same value and the verification will be successful. So in this case, the attack to message integrity will be successful. And this attack was possible because you are using a standard hash function. And essentially it is because there is no key involved. So when using MAC, it should be intuitive by now. Even though when Mallory tries to modify the message M prime, without having the correct MAC key, which is used by Alice to compute the MAC, this Mallory guy will not be able to compute the correct MAC prime value without using the correct MAC key. So what will happen is when Bob receives the M prime and the MAC prime, he will use the hash function, the same hash function, but he will also use the shared secret key, which is known only to Bob and Alice, and then compute the MAC value, and then compare against the MAC that he received. Of course, these two MAC value will not match because after all, Mallory didn't have the correct MAC key. Even though he had to attempt to find a random MAC key and then use the key to compute MAC prime, it is very likely that the verification will fail. Notice the specific term that I use here. I only say that it is most likely that verification will fail. I did not say that it is not possible that the verification would be successful. because there could be a case that Mallory guy somehow was able to find, even though he randomly generated, he was able to find the correct key, which would result in the correct MAC value. And then in that case, the verification will be successful. So what I'm trying to say here is, although MAC can be typically used as the message integrity proof, MAC has the limitation, which is that MAC is subject to brute forcing attack. Brute forcing attack means that the attacker can simply try to find randomly likely possible keys and then use it to compute a MAC value and then compare against the MAC that he intercepts and then see if they match. And he can do this repeatedly until he finds a match between the computed MAC versus the MAC that he received. And then in that case, he will know that he found the correct key, correct MAC key, which is supposed to be shared only between Alice and Bob. And that attack is known as brute forcing attack. And this brute forcing attack here is possible because hash function is known because it is a public knowledge, and MAC value and M is known because if you recall the previous slides, so as shown in this slide, message M and MAC is transmitted over a public channel, which can be intercepted by the third-party attacker. And in that case, this Mallory guy may have the knowledge of both M and MAC, and he also knows about the hash function that is being used because it is supposed to be public knowledge. The only thing that is missing is a key. So essentially, he can do the brute forcing to find the key that will produce the match between the computed MAC versus the received MAC. So in this case, we have to find a way to address this problem. And the root cause of this problem is that because in MAC, only the message is being hashed. If you look at the function, so this message is the one that is being hashed, of course, by using a key, but this key itself is not being hashed. This key itself is not being hashed. Message is the one that is being hashed by applying a hash function. The key itself is not hashed. So in that case, the way to address this problem is simply by adding another additional layer of MAC again. So what I'm trying to say is you compute MAC just like before. Compute the MAC by applying a suitable hash function on the message by using the key K, and then add another layer, take the resulting MAC value, and repeat the same process. And this is the same process. The only difference is right here. It replaces the message M. And this resulting value is called HMAC because it hashed the MAC value. So essentially, what is happening here is in the HMAC, both the key and the message are hashed. In the MAC, if you look at it, only the message is being hashed by using a key K, and then this MAC value is being used to hash again. And since MAC value encapsulates both the key and the M, the hash value, the resulting hash value is basically contains the hash of both the key and the message. Essentially, in HMAC, I repeat, both the key and the message are hashed. And depending on the kind of the hash function that you use, there can be barriers, there can be variants. For example, if you are using MD5, you can denote it as HMAC-MD5, or you can also be using SHA-1 or SHA-2 or SHA-3 and so on. And those are variants of the HMAC functions. So to recap, MAC is a tag used to authenticate the message and verify the message integrity. MAC is also known as a keyed hash function simply because it is a hash function with the key. MAC provides both integrity and authentication services. It does not provide confidentiality, however. MAC may be subject to brute force attacks because only the message is being hashed, not the key itself. And HMAC provides better security because in HMAC, both the key and the message are hashed. That will be all regarding MAC. Thank you very much for your attention. See you next time.